of the afternoon is modular task learning in an embodied two-dimensional visual environment.
Hi, everyone. I'm Kevin Feigelis from Stanford, and today I'll be speaking about modular task learning in an embodied two-dimensional visual environment. So when we speak about the neural basis for behavior, what do we mean? So far, we're beginning to understand how sensory systems like vision encode representations of their stimuli. So the ventral stream is thought to act as an information reformatter, where along each stage in the visual hierarchy, images are abstracted into more usable forms. And those abstractions can serve as an effective basis for solving various object recognition tasks. And we're going to call those readouts. Now, thanks to recent work, we're beginning to know how to model some sensory systems. For instance, we know that deep convolutional neural networks are reasonable approximations to the ventral stream. Now, we can also train these powerful networks to accomplish many things, but often they're restricted to just a single behavioral readout at a time. Now, when it comes to decision making, we know that animals and humans don't share these same limitations. And that's a key gap in what we're currently capable of modeling. So, how is it that given our entire lifetime's worth of knowledge, we're able to flexibly choose what the most appropriate readout is at any one time? Today, we're going to build upon two ideas to start creating a flexible model. The first is going to be the concept of a modular learning approach, and the second is going to introduce the touchscreen as an embodied learning system. So, if deep convnets are a guide for what visual processing is like, then we probably don't want to train a full visual system for every task, because full visual systems, like a deep convnet, are probably really slow to train and expensive to compute. So we only really want one of these, and we only want to use it once per stimulus. Instead, we can choose to allocate a lightweight readout module on top of the convnet, which should be easier to train and take fewer examples and function on a task-specific basis. But almost more importantly than finding a module which learns its own behavior quickly is that you should be able to learn from it quickly, because that's going to ensure that a long time down the line, when we have thousands of modules reading off the convnet, the tasks which might have seemed impossible to learn from scratch are now easier to decompose into combinations of previously known behaviors. But let's say you know exactly the right module to build for every task. There's still an issue in that, and that's that each task you encounter might require its own decision structure. So if you started with binary classification, then you'd probably start with 2 decision units. But if you want to add some more classes, then you need to somehow add more decision units. And if you wanted to do quite a different task, for example, localization, then you'll need to change your entire readout structure from predicting discrete values to continuous quantities. So how do we deal with potentially different decision structures in a coherent fashion? That's going to lead to idea 2, which is having our lightweight readouts interact with the touchscreen. So I know I keep using that phrase, but what's so great about these devices? Well, for starters, they're kind of pervasive in our society at the moment, and they don't look like they're going out of style anytime soon. And all you have to do is poke them. And that's the flexibility that we're talking about here. Thousands of tasks, but just a single decision structure. Additionally, experimental labs are already using touchscreens to study complex behavioral mechanisms. And here we're watching macaque interact with one. So a core goal of this work was to computationally model the touchscreen setup as closely as possible to the real world, or at least this real lab scenario. And our idea was to model this through a server-client pair, where the screen is going to be the server and the agent is the client. On every time step, the server sends the agent an image stimulus and a reward based on previous actions. The agent is going to respond with a touch, which is one action chosen out of all possible screen pixels. The server's program uses that to then compute what the reward should be on the next time step. The agent is a neural network learning to best choose its touch actions to maximize this reward. So let's consider stimulus response, a single screen object categorization task. We began with this one because the paradigm is already common in real neuroscience experiments, and it requires no working memory in terms of the model. So here, every class is associated with a specific on-screen region, where when one of its instances appears, the agent needs to poke inside. So here we're looking at a dog right, butterfly left scenario, where the reward maps are going to have blue for low rewards and red for high rewards. Another classification analog is going to be the match to sample paradigm. We chose this one because it's a good test of the model's working memory and its understanding of local image structure. So here, the agent first sees a sample screen, which tells it what the correct class is for this trial. Without being rewarded, it then advances to the match screen, showing one or more distractor classes. To be rewarded, the agent must first recall the class from the sample screen, then find that class's box on the match screen and poke inside it. And lastly, we have object localization, an excellent task for requiring the model to be really precise in its poke placement. Here, it needs to poke in two opposite corners of the on-screen object to predict a localizing box around it. And that's going to differ from the previous two tasks because your actions in the future are going to strongly depend upon what you're choosing right now. And there's a wide variety of tasks that we also chose to study with different difficulties. So, for instance, stimulus response, you can add more classes and further partition up the reward regions. Match to sample, you can take the boxes on the match screen and randomly shuffle them around, or you can add even more distractor classes to the match screen. So ultimately, there's a wide spectrum of potential touchscreen task variants encompassing many different experimental setups. So when you're looking back at how these networks were to behave traditionally, it's really clear what the core utility and challenge of this unified touchscreen interface is. It makes the agents learn these readouts in an emergent fashion, because at any point in time, it actually has access to tens of thousands of choices. And it's its job to learn how to effectively narrow down this massive decision surface into something small, something that may seem binary, even though it really isn't. Because that's how animals do these tasks, and that's how we would do them. And we're pretty good at that. And that's exactly what we're attempting to model here. So our agent consists of a fixed visual backbone, which for our purposes is going to be a pre-trained deep convnet. On top of that are our lightweight readout modules. So those are also going to take in their own action spaces features, and that's how we solved that hard reinforcement learning problem of a large action space. So using the action and image features, it then predicts a reward map over the whole screen. A sampling policy takes this to determine what the best action is to return to the server for that frame. And just briefly, what they're actually learning is an expected reward map for a few time steps in advance, and the error signals for these are going to be back-propagated and learned through gradient descent. And the action sampling itself is reminiscent of Thompson sampling, but I'm going to spare you the details. If you want some more, I can go out over it after, or you can just pull me aside later on. Okay, so that's a lot about the general setup. But I haven't yet told you how to actually start building these lightweight readout modules. And that's really the core point of this work. We know that they should be small, learn quickly, and support fast switching. So the question really becomes, what generic architectural principles do we need to uncover that can meet all these criteria? So for inspiration, let's go back to binary SR. Now, if I told any of you to solve this task, you'd find it trivial. But you would probably partition your solution into two parts. The first corresponding to the class, and the second to the direction. And once you guys know how those two interact, somewhere in your brain, you just created a module which computes something like this. Your brain created a formula saying that the reward on this task is purely a function of those visual features F and only the X component of the action. But it says that you need to first reduce down the large space of those visual features in dimension independently of the action space by using some vector. And we're going to call that C for the learnable class boundary. The actions themselves come in later, but they're multiplied in. And building that formula into a neural network and having its only learnable parameters be that class boundary, it would learn those nearly immediately. But that's just a specific case, and I've used a lot of human intuition to build it. We want to generalize this. So what about this equation can we take with us to start building a generic readout module? First, we see that there's an early bottleneck, where the large dimensional visual features are reduced in dimension before considering the action space. Next, we see that the actions enter in through a multiplicative interaction. And lastly, we see that there's a spatial symmetry involved in the formula. So building on these ideas, we constructed modules which use none, some, or all of these concepts to see whether they would scale to tasks in a generically learnable fashion. So first up, we'll describe what we're calling an RS activation, which concatenates on the squaring operator to the standard ReLU nonlinearity. So of course, by the universal approximation theorem, this squaring operation can be approximated by a large sum of neurons using more standard activation, such as just this ReLU itself. But by using the low-order polynomial directly, we're able to then build much smaller modules, but with the same expressive power. And what's going to follow is what we call the LRS architecture, where those large visual features are reduced in dimension through a standard linear transform before being combined with the action space with this RS nonlinearity. And the reason we do this is because that formula from before is a special case of this with a small number of parameters. We also compare this with early bottleneck LX modules, but using more standard activation, such as ReLU, 10H, or sigmoid. We also experiment with just using the squaring operation alone, as well as some more modern activation functions. In contrast, we make the analogous late bottleneck LBX modules, where those large visual features are directly combined with the action space before any bottlenecking has been done. And lastly, to factor in symmetry, we take the base ReLU nonlinearity and concatenate on the square of both of its terms. This is what we call the Cre-S, and it's going to bring us all three generic principles. So let's see how these models fare against our tasks. First, we're going to compare them against the formula encoded network that we just saw. So the module which makes no use of multiplicative interactions really struggles to solve this task. Its learning curve is nowhere near the formulas. But the LRS, with its polynomial activations, begins to recapture much of that lost speed. And the Cre-S, with its symmetry prior, brings us really, really close to that original speed displayed by the formula encoded network. But this result is just for a single task. Our main result is that these same generic principles scale across many tasks in this touchscreen environment, and they did so for every single one that we tested. So I'll plot four more learning curves here. Binary SR again, the four-way version of it, a challenging four-way match-to-sample task, and localization. So we tested the late bottleneck in three sizes: small, medium, and large. So small is going to correspond to the same size as our early bottleneck modules, but we see that it really has some trouble converging. The large version, however, that one seems to do pretty well, so that's sort of as expected. But just by reducing down those visual features early on, the LX can start to outperform in some scenarios, but it also seems like it sometimes has trouble. But looking at the LRS with its polynomial activations, we see that it tends to display some really sharp rise times and plateaus at higher final reward values. And that's only beat by our Cre-S with its symmetry. So this match-to-sample task is an excellent example of how much more efficient it can be. And taking the area under all the learning curves for all 24 modules we tested across all 12 tasks, that's even more apparent. But this is a lot to take in, so I'm going to average across the tasks. All right. So now we're able to see that modules using all three generic principles, like the Cre-S, beat the competition hands down. And those that are just merely multiplicative, like the LRS, do marginally worse. But for an LBX to come even close, it needs to be significantly larger, and that's going to hinder it at switching. And even still, it doesn't come close. And I'll show you why that hinders at switching in a second. But first, I want to plot some time evolutions of the predicted reward maps, because this is really where visualization is at its peak in this project. Because it's an excellent representation of seeing how the agent is learning the interactions between these image spaces and the action spaces. Because you can see around the initial stages of learning how unsure it is of the actions it's taking before it begins to refine those reward boundaries. And lastly, we tested the LRS and the late bottleneck module under some simple switching scenarios. So here, this blue trace is going to be the LRS trained on the base binary SR task, and this green curve is going to be the same module repurposed to solve the reversal switch, where the left class is now the right class and vice versa. This red curve is going to be the same LRS, but repurposed to solve the switch to a task where it needs to know two entirely new classes. But whereas we see that the LRS shows a large improvement after being trained on a similar task, the late bottleneck offers little gains over even just retraining it from scratch. So even though we saw that on a single task it may have performed all right, its large number of neurons actually hinders it from learning anything new. And that's even starker when we look at the match-to-sample switches, where it fails to even think about converging within the small time frame necessary to study task switching. All right. And that's going to bring us full circle. So embodiment made our entire question space richer and exposed a core challenge as to how to actually build our lightweight readout modules. In itself, that opened up an entirely new domain of modeling questions. And that's going to be like, what are the generic properties of the decision structure? We saw 3 today. There was the early dimension reduction, polynomial activations, and spatial symmetry. But there's likely others out there. Just using the ones that we found, we're able to design some architectures which are not only efficient on single tasks, but across similar tasks as well. But that's just the first step. We'll also need to know how to actually switch between our learn modules, or even before that, when the proper moment is to allocate a new one. There's also the question of the optimal method of reuse of old modules knowledge, as well as when we have a lot of them, we'd like to consolidate those that are functionally similar. And I've only spoken about the first one, but moving forward, we're working on tackling the rest of the full stack continual learning system. And in addition to this computational work, we're working hard on some experimental collaborations with Jim DiCarlo at MIT and Mark Schnitzer at Stanford, where we'll be comparing our modeling experiments against real neural and behavioral recordings in rodents and primates. So I know this was a lot to take in. So we have a full version of this up on archive that please feel free to check out. And if you have any questions about this, feel free to email me whenever, whatever, and pull me aside at the poster session if you want to. So thank you. No, that's okay.